Hello everyone. So in today's video, we're going to wrap up our section on exponents, talking about what we call exponential growth. So hopefully you got a chance to look at the last lesson where we were drawing some exponential graphs and you got to see what they look like and compared those to other models that we use. Today we're going to now put that into practice. So the example I'm going to start with is this. 5 students come to school with a cold. Every day as the cold spreads, the number of students with the cold doubles. So we're going to fill in this table here and then draw a graph to see what does this look like day by day. And then in the end, we're going to try to come up with a way, can we calculate how many students have colds without having to do all this work here? That's where we're heading. So I'm going to start on day 0. It says students show up with a cold. So before any days have really occurred, what we have is that there are 5 students that have this cold. So this is not on day 1, but this is then after 1 day. So they initially show up on day 0 with 5 students that have a cold. After 1 day has passed, the number of students will now double. And as another day passes, the number of students will then double again. We just continue to go down the chart here. Another day passes and the number of students doubles again. Another day passes, the number of students doubles again. Another day passes, again the number of students doubles. And then I went up to day 6 where the number of students doubles again. So what we see here is that we start with some small values, but at the end we start to get big, and we get quite big quickly here. If we were to do another, we'd already be up to 640, and do another day, we'd already be up to 1,280 students. So in the end, we start to see things grow very, very quickly. Because of that, I had to pick a scale here where I'm actually counting by 50s for the number of students. Again, days would be then our x variable, and number of students would be our y variable in this case. So on day 0, we have 5 students. So that's really small. In fact, with this scale, that's hard to even plot. In day 1, there's 10, so only slightly bigger. Day 3, there's still only 20. And remember that this scale, one block is 50, so 20 is not even halfway through that block yet. On day 3, we're up to 40, so now we're almost there. So now we're just under that line. And then finally on day 4, we get to 80. So now we're just under the 100 mark. Day 5, we're now up to 160. So there's 150 and 160 just above that. And then on day 6, 320. The scale that I picked just puts us just barely off the top of our graph. So what we see here is if I connect these is that we're actually quite flat here for the first little while. And then all of a sudden this starts to pick up. And then we're going to see this grow here quite quickly. So that's when we look at these exponential graphs, what happens is that we're flat for a little while, but then once it starts to curve up, it starts to grow quite quickly. Now, in this question, the second part, then it says, well, can we come up with an equation or a way to calculate how many people will have this cold? Let's say we wanted to look at day 10. Would I have to go through this whole table to get to day 10? And the answer is no, we don't have to. We just have to look at how are we calculating each of these. So on this day right here, we were taking that initial value of 5 and we multiplied it by 2. And then on this day here, we took the previous value, 10, and we multiplied it by 2. But instead of writing this as 10 times 2, what I'm going to say is, well, here's how we got the 10. The 10 was 5 times 2. So there's our 10, and then we had to multiply it by 2 again. And if we start to see now maybe a bit of a pattern develop, if I wanted to get 40, I would have to take 20 and multiply that by 2. Well, to get 20, we did this. So I'm going to rewrite that, 5 times 2 times 2. Okay, there's our 20, but then I had to multiply by 2 again. I had to double that again. And if you keep going through the table, we'll get this same idea again. To get 80, I had to take the previous value, 40. Well, there's how we calculated 40. 5 times 2 times 2 times 2. And then we had to multiply that by 2 again. And if we continue this process, okay, through the table, this one then 5 times 2 times 2 times what do we have here? Times 2, times 2, times 2, times 2. Okay, there's my 80, and now I have to multiply by 2 again. Now, I'm getting tired of multiplying all these 2's or writing all these 2's out. So this last one I'm going to short form and say, well, I need to multiply by 2. Here we multiplied by 1, 2, 3, 4, 5 2's. So if I multiply by another 2, here is now the power of using exponents, is that I can just write that as 5 times 2 to the exponent 6. And we could go back here and say this one is 5 times 2 to the exponent 5, 5 times 2 to the exponent 4, 5 times 2 to the exponent 3. And if you look closely, there's a nice pattern here, because how many 2's am I multiplying by? I'm multiplying by 6 2's. Why? Because I'm on the 6th day. Here there are 5 2's. Why? Because I'm on the 5th day. Here there are 4 2's. Why? Because I'm on the 4th day. And so on as we work our way back. So if we want to figure out how many students there are, so remember that y was our number of students, I'm going to take y, and each time we have 5, that initial number of students, and we're multiplying it by 2. And if I try to write this in general, I'm just going to say, well, I'm writing it to whatever that x value is. Whether that x value is 6 or 5 or 4, that's our exponent. So the number of students is 5 times 2 to the exponent x. And this part should look familiar because this is what we've been graphing here over the last couple of days as we've been comparing some different graphs on Desmos. Okay? The only part that we're changing is that we're now adding in this initial value of 5. So this is what our exponential growth will look like. It describes an exponential function, which we've been graphing, that starts very slowly. That's what we always see. It's quite flat at the beginning, but eventually will grow quite quickly. And this type of growth is observed. We see this in many real-world scenarios. Right now we're seeing it with the coronavirus, that this is the type of growth that initially the coronavirus was doing, and then the idea was we were trying to flatten the curve. So we were trying to stop this from doing this. The world was trying to get to this point, but we were trying to flatten this out and eventually hopefully bring this back down. So what we see is that when we write this in general, that the a value, in this case is that 5, that is our starting value. Start or initial value. What we see is that b, in this case, we multiplied by 2. We call that our growth factor. That tells us how fast this thing is going to grow. Is it going to double? Is it going to triple? Okay, and that was important research that they were doing as they were looking at the coronavirus as well, as how fast are things growing. And then n, in our example, was how many days had passed. But if we generalize that, it might not always be days. It could be weeks or months or years, usually some measurement of time. So in general, we just call that the number of growth periods. How many growth periods have happened. So on day 6 in this example, we had 6 growth periods that had occurred. So if you look at a slightly different example, in this case, something worth some money, Steve had bought a rare coin that's worth $500. It's going to increase in value by 4% each year. Okay, so instead of doubling something like this here, this time we're going to have to look at, well, what do we do with this percentage? The value of the coin, V, can be modeled using this equation. Okay, very similar to this here, where n is the number of years. In other words, again, here is that idea that 500, there it is, there's our initial value, or our starting amount. Okay, n this time is number of years instead of number of days. The part that looks a little bit different is this here, because here we had this 2 because we were doubling. So just quickly, why am I doing this here? Well, this comes from the fact that if this coin was going to keep all of its value, we would say it keeps 100% of its value each year, if it was just going to keep its original value. However, in our example, this is going up by 4% each year. So it's going to keep 100% of its original value, but it's going to add on 4% more. Now, if I convert those to decimals, remember to convert a percentage to a decimal, I will divide by 100. So if I divide that by 100, I get 1. If I convert this to a decimal, if I divide by 100, I will get 0.4. And if I add those together, I get 1%. 0.04. So it's 100% of its original value, and add on 4% more is the same as saying multiply by 1.04. So if he plans on selling this coin in 20 years, how much will it be worth? So now I don't need to fill out the whole table like I did here. We can do this very quickly. We can say the value of the coin is initially $500. We are growing this by 1.04, 104%, and we're going to do this 20 times for 20 years, the same way the exponent showed up here. And then we can go to our calculator to get a value. I've already done it so that we can work through this quickly, but we end up with this coin being worth $1,095.56. We can also take this then and use this idea to expand on our understanding of these equations. Let's say that he had a second coin that was worth $400, maybe a little bit more rare, something different, so it's going to grow a little bit faster. It's going to grow by 6% each year. So now let's write the equation for this coin. So very similar to this one, I'm going to say value equals, initially it is worth $400, so there is the initial value. What are we multiplying by? Again, the idea here is that it's going to keep 100% of its value, but we are going to add on 6% more. So if we do that, we have 1 plus 0.06. If I convert the percentages to decimals, add them together, 1.06. So there is the equation now for this second coin. And this just allows us then to calculate things very quickly. We can say, well, what's the value of the coin in 10 years, 20 years, 30 years, 5 years, 2 years, doesn't matter. We could very quickly go to our calculator, put in some value for n, and we can figure out what is that value, or that the coin in this case, very, very quickly. To finish our note off, the last piece, I just want to look at two quick examples here, and that is how do we come up with these equations then. So in our first one, write an equation that represents each of the following. We have a city that has 45,000 people, so there is our initial amount, and it's growing at 3%. Okay, so as a decimal, 0.03. So if I want to calculate the population equals, by the way, you can put whatever letter you want there. I sometimes try to pick one that describes what we're calculating. If you always just want to put y there, that's fine as well. We always start with the initial value. So initially there is 45,000 people. What are we growing by? Again, we take this and we add on 100%. If I do that, we end up with 1.03. If you want to see that, we have 1 plus the 0.03, if I write them as decimals, to the exponent n. In our last one, we have a colony of ants that's going to triple in size each week. Okay. Initially, there are 2,000 ants, so there is our initial value. So as we write this, I'm going to say A for ants, so A equals, we always start with our initial value, 2,000 ants. This time, there's no percentages. It's back to this idea where we started when we were doubling the number of people with a cold. This time we are tripling. So for tripling, I'm going to then multiply by 3. So two ways we have this, as a percentage or some descriptor like double or triple or quadruple will be there. And then we just have our exponent n, where n then this time is number of weeks, where here n is the number of years. So it's whatever that time period is. Hope that helps. I've posted an assignment. There are 4 questions for you to try that look similar to this. Again, you can type them right in the assignment and submit it that way if you want, or you can print it off and do it on a separate sheet, whatever works for you. This is the end of our exponents section. Next week, I'm going to do a couple lessons on probability, and that will take us to the end of the course. If there's any questions, please let me know. You can send me an email, and we can set up video chat if we need to, if you want some extra help. Have a good day, guys.